The question here is, what is capillary pressure and how does it apply to stresses in soil? If you recall from your basic physics, if I take a tank full of water and insert a capillary tube in there, the water is going to rise in the tube, right? Called the capillary rise. Let's understand this a little bit more. So I made some graphics here. I have drawn this tube to an exaggerated scale so you can clearly see the forces acting on various parts of it. And I have taken this part of the water column and completed the free body diagram for that. Since points A and B lie at the same elevation, the pressure at point B must be the same as the pressure at point A, which is atmospheric pressure. So I have marked that over here. Then we have the weight of the water column acting vertically down. What is holding this water column is the capillary force Ft. I'm going to assume the tube to have a circular cross-section, and therefore this capillary force kind of goes around in a circle like that. We still have the atmospheric pressure acting on the outside like this, and then the capillary force is a function of the surface tension. Surface tension between water and the material that the tube is made of. If you integrate this atmospheric pressure around this surface over here, in order to find the vertical component of it, you will find that it's going to be exactly equal to the force due to the atmospheric pressure at the bottom of the tube. So they are going to balance each other. So on that free body diagram, what is left are the capillary force Ft and the vertical weight W. Let's go ahead and write down a vertical force equilibrium equation for the free body diagram. W equals Ft cosine alpha. The height of the water column varies along the meniscus, but taking an average height as h of c, then the weight of the water column equals volume multiplied by the density of water, denoting the surface tension by T, where T is the force per unit length. You multiply T by the circumferential length of the circle, which is 2 pi r, you get Ft. Surface tension of water in SI units is this. We will make use of this number in an example a little later. So you simplify this equation, we get this for the capillary height. If the tube is made of clean glass, then alpha is 0, and then the height of capillary rise becomes equal to this, 2 times T divided by gamma, so W times R, where R is the radius of the tube. We also need to know a little bit about the variation of the water pressure within the water column. We know the pressure here is atmospheric pressure, right? And if you go down, the pressure increases. But if you go up, the pressure decreases. And therefore, the pressure within the water column is negative. In other words, pressure inside the capillary column is negative. This picture shows schematically how the water pressure varies on a vertical line inside the water column. So at point B, water pressure is 0, and as we go from point B to C, it decreases linearly. At that point, at the top of the capillary column, that is at point C, the water pressure is minus gamma W multiplied by H sub C. And then, of course, if you go below point B, we still have the normal water pressure, positive water pressure like we typically have inside a water table. And this is the most important point for us, because now we're going to take these ideas and apply it to real soil, and we're going to find that a portion of the soil is going to be under negative water pressure. So now let's talk about how to apply these capillary principles to real soil. So here's a sketch of a typical field soil deposit. We know we have interconnected pore space between particles, and these interconnected pore spaces act as capillary tubes. Water rises through these capillary tubes as shown in red over here. Size of these pore spaces are different, and therefore the capillary tubes don't have the same diameter. So the capillary water is going to rise as high as it can be sustained by the surface tension. This equation we derived earlier shows that the capillary height is inversely proportional to the radius of the capillary tube. And therefore, in tubes with smaller diameter, the height is going to be bigger. Here's a little schematic of the meniscus at the top of capillary columns A, B, and C. The radius of the meniscus is smaller here at point A than at point B, and at point B is smaller than at point C, and therefore the height of capillary rise is different in these three columns. The height is greater at point A than at point B, and then at point B is greater than at point C. So the bottom line is it's somewhat complicated, but nevertheless, water is going to rise through these pore spaces. So if you were to plot the degree of saturation above the water table, you will find that it'll look something like this. In other words, near the water table in a zone, the degree of saturation is going to be 100%. But above that, it will decrease a little bit, and then it'll become completely dry beyond a certain height. It can also be easily understood that the pattern of variation of the degree of saturation within the soil layer is going to depend on whether the water flows downward from a rain or water rises from water table. If the water flows down due to rain, you will see that a larger part of the soil layer will be saturated. On the other hand, if it rises from a water table, the capillary height is going to be a little smaller. Simplifying these ideas, we can say there's going to be a zone above the water table where the capillary action is going to take place. And this zone is called the capillary zone, and we know the pore water pressure is going to be negative in that capillary zone. And the negativity is going to increase as you go up from the water table, being the maximum at the top of the capillary zone. The next question is there a way to have some idea of the capillary rise in real soil? Well, we can use this equation right here, but this equation requires a radius. In other words, we need pore radius, right? But the pore radius is going to depend on the particle size, but we know most soils have a distribution of particle sizes. So how do we come up with a pore radius? So what is normally done is to assume that the pore diameter is 20% of D10. With clay soil in mind, let me assume 1 micron for D10. Then the capillary radius is calculated to be 0.1 times 10 to the minus 6 meter. I gave you a value for the surface tension before in SI units. We know the density of water is 9.81 times 10 to the power of 3 Newton per meter cubed. So I substitute all of these quantities in our basic equation for capillary rise, and I come up with 150 meters. You probably wouldn't have guessed that number, right? Water can rise 150 meters from the water table in a typical clay soil. What about the pore water pressure in the capillary zone? Well, at the top of the capillary zone, the pore pressure is calculated to be about minus 210 psi, so that's a pretty high negative value.